Hey, good morning, folks. Welcome to our first uh, AI live stream that we are doing with Priyanka. This is our first experiment to see can we do more of live streaming and get the users involved much more actively. So for today's topic, we are going to look at NLP. And over the course of next few weeks, we are going to take a deep dive into NLP. But this is just a starters topic to get you started. With me is an upcoming MVP, Microsoft AI MVP, Priyanka. We have done a lot of these sessions together, and I will leave it to her to do her introduction and walk you through this fantastic topic of topic modeling and take it up from there. Priyanka, over to you.
Thanks, Setu. And a very good evening, guys. Thanks for joining us. And we are sorry for the break in between, the hiatus in between. And as you can see that we have been, announcing a lot of events. So we announced sessions for enforcement learning. And as we posted on the announcement board, we'll also be coming up with the sessions on virtual reality, augmented reality, deep learning. So please do keep a lookout on our meetup page for more announcements. And for today's session, we'll be discussing about LDA, which is Latent Dirichlet Allocation, and it is a natural language processing technique used for topic modeling. So, what is the need for this? Why did we, come up with this particular session? And we'll go through it with real life use case which we have implemented in our workplace. Brief about me. So, excuse me. So I am the head for innovation and regional head for data science in emerging markets. I work in Franklin Templeton. I am also the architect for AI-based landscape solutions, big data projects. Yes, a full stack developer, and I am also a public speaker, blogger for AI ML technologies, especially centering around Microsoft stack. And you can always reach me on my Twitter handle, which is FuzzyMind1. All right, so let's start. Before we actually jump into topic modeling and latent dirichlet allocation or LDA, which it is commonly known as, let us see that why did we think of going down the topic modeling way, and what are the things which are existing solutions like Elasticsearch or cognitive search were not able to answer. All right. So before I go to the LDA, let us see what we initially had, a bit of context of about our problem statement. Okay, so in emerging markets, you typically have analysts who will go on calls on companies, so they'll collect information about companies in various sectors, so real estate and energies, utilities, finance sectors, and they will come up with recommendations about that company, so that the portfolio managers can take a call about investment, whether we should keep a watch on the stock or advise clients for investment. Because as you know, my company, they deal with asset management, mutual funds also. So all these information is very critical. The analyst input about those companies is very critical. So that is something which is called as a call report. So call report, it contains information about analyst's recommendation regarding company. So it's not a very huge text document, maybe like around a few kilobytes. Yeah, but it has comprehensive information. And over the years, so we have data of around 10 years now, and over the years we have collected around more than a point 0.5 million call reports. Okay, so they are sizable in number. And then what we did was we built a document text search engine using ALK stack, Elasticsearch. And what we did was, now the analysts or the PMs, whoever is there, they should be able to search keywords from that huge corpus. So around zero point 0.5 million corpus text documents available with us. They should be able to search keywords. Okay, and this is how it goes. So I'll just show you a brief functionality of how it works. All right. So our call report that way is very, how should I say, efficient. So it not only gives me hits on exact keyword match, it also gives me suggestions. For example, say I'm searching for Tata. Uh, Yeah, so it gives me suggestions about whether I should search for Tata head office, Tata Power, Tata Chemicals, Tata Tea, and stuff like that. So this we have a type ahead search or suggestions, search elastic suggestions. We have built on a few fields, which is like the author name, the name of the analyst who is writing the call report, or the location of the place which the company is situated, the name of the company itself, and a few other geographical region, country, and all those things. Okay. So, for example, if I'm typing Thai, and yeah, so you get Thailand, Thai Airways, which are few of the fields which we have configured for type ahead search. Now, let's say I want to select something which is let's say electric car. All right. Okay. And yeah, and like this, and then I immediately get hit. So you see that the elastic search itself is very efficient, about more than 5,000 results in 0.64 seconds. Okay. And I get pretty good approximation of my results. I can get terms where electric car together is not a search term, but then it may be a bit apart, like electric and car, or maybe just mini car. Still, it gives me those kind of hits. So our existing Elasticsearch, it satisfies the purpose of identifying fuzzy search. So if I'm mistyping something, if I was trying something like this, eclectic car, for example, okay, it will still try to approximate my search, and it will try to still come up with the electrica, for example, and then it will try to correct my fuzzy search and give me back cognizant call results, relatable call results. So far, so good. The problem surfaces when the problem, okay, just let me go full screen again. All right. So what we had was working for us. Analysts were able to do search among this huge number of documents, and were able to find not exactly not matching terms, maybe words far apart. Like oil price is not a word together, but oil and price are two distinct terms. Yeah. So it was working for them. But what about searches when it comes to related terms? For example, if I'm searching for something like driverless cars, okay, then it should also give me results about self-driving cars, robotic cars, energy, green cars, energy-saving cars, example, which essentially mean the same thing. Or let's say if I'm trying to search for particular metal like lithium, and maybe that particular word is not there in all the corpus which I have right now, but maybe there are certain industries which are making use of lithium, like for example, dry cell, right? So energy sector, utility sector, or if lithium is not searchable, it should prompt me that lithium was not found, but hey, do you want to search for other metals related to lithium? All right. So those kind of related search terms, because imagine that zero point 0.5 million documents, and the documents growing day after day, because analysts will come up with new call reports maybe every day, every single day, and then that adds to the amount of documents, and then searching through that much corpus and coming up with keywords, it's very hard. So that's why analysts wanted to PMs and analysts wanted to look at something which is can give us semantically same words. So if I'm typing for, let's say, copper, iron ore, then it should also give me recommendations about where you're looking for this term, or people who searched for Tmall also searched about maybe Taobao, or people who searched for Nike also searched for Reebok prices, something of that sort. So people want recommendation, people want semantic analysis, people want sentiment analysis, people want related search terms. So all these things and much more are possible, or only possible to a certain extent with offerings like Elasticsearch, or with offerings like Azure Cognitive Search. And that's why you have to go beyond, over and above that, and try to build your own machine learning model that is modeled on the lines of word to wake, or modeled on the lines of topic modeling, to identify this thing. Okay. Now certain other constraints which we had was, so as I was saying, huge number, humongous amount, distributed across 11 sectors. So we have financial industry, we have uh, government controlled sectors, real estate, we have utilities, we have minerals, all those things, right? And then new call reports being added daily. Impossible to go through each document. Now if you have experimented a bit with Elasticsearch or Azure Cognitive Search, you have a functionality which is called as document tagging. just forget about Elasticsearch and stuff. Whenever we write a blog articles, right, you still are asked to tag certain keywords to your article or document so that it is easier to search through them for search engine optimization or for search engine to identify the document. These tag words are used. So maybe if a particular document is talking about insurance claim policy or those kind of things, then maybe I should identify such tag words and tag all those documents which talk about a particular theme accordingly, right? And this is also, you can tag documents, and then it will be easier for Elasticsearch or cognitive search also to come up with related documents. But then how do you go through almost like 550K documents and then come up with tag words, and then the onerous task of re-indexing them or re-identifying tag words maybe after a month or 2 months or a year, right? And then how to establish word semantic relationships. So basically, when I'm talking of self-driving cars or robotic cars, they mean the same thing. Or how to build a taxonomy, right, for all the documents. So I want to build my own dictionary where I want to say that, hey, if this documents are talking of reinsurance or insurance or claim or policy or premium or policy premium, they are essentially talking of insurance, a theme called as insurance, and they all should be clubbed together. Or a person who is searching for these documents should also be able to search about, if a person who is searching for policy or claim should also be able to search about documents which are talking about related words. So I should be able to build my own dictionary on these lines. That brings us to why we went to LD and why we looked up for neural word embedding and why we went on to natural language processing techniques. Okay, so our complete solution architecture, in a nutshell, it looks like this. So what you do is, for all the documents which we have, the 550K odd documents, you identify the topics using LDA, which is our focus today, how we did that. Then build the word taxonomy using the topics and the words. So build our own dictionary, which says that, hey, when they talk of politics or when they talk of, for example, energy sector, then maybe in energy sector, these keywords fall in this category, and all the documents talking of this thing should be tagged to this particular keyword or this particular topic. Okay, so this is a taxonomy which we built. Okay, so this is the example I've given, like insurance premium policy can be added as synonyms. And then you use Azure Cognitive Text Analytics services to get the sentiment for each document. So whether the sentiment is negative, let's say I'm talking of declining trends, let's say I'm searching for losses or market downtrends. So then, which means I need to identify a set of documents which are talking of that sentiment. Now, downward trend or losses or declining trends are all a bit negative sentiments, right? So then we are using Azure Cognitive Text Analytics to get the sentiment for each documents, to identify the named entities and to get some contextual information and key phrases. Okay. Then the key phrases which we are using that as tags. Tags meaning, as I explained earlier, that tag the documents for particular words to search those particular words. Then we feed these tags and synonyms to Azure Cognitive Search. And then we iteratively refine our dictionary. So today, maybe I built a first level taxonomy where I'm identifying these keywords, insurance, premium, policy. Maybe tomorrow, I might refine this taxonomy further if I find that in insurance, premium, policy, claim, and these things, there are maybe, legal battles, legal tussles, and those information themselves can be, or frauds, insurance frauds, those that taxonomy can be a different set altogether. So we iteratively keep on refining every fortnight or every month, depending on the precision which we are getting and depending on the number of call reports which are added by the analyst daily. Okay, so before we jump to LDA, the basics of LDA, I just want to also show you about how we are getting using the sentiments from Azure Cognitive Text Analytics. That would be a separate session altogether. This is just a teaser for what all capabilities Azure Cognitive Text Analytics services expose us to. Okay, so you go here, and let's say this is the demo site of text analytics. So basically, I'm not typing anything. They have given some corpus here, some text here. I just click analyze. They have trained their models on NLP techniques. And basically what you get back is an analyzed text which gives you sentiment, overall sentiment of the document, of sentiment per sentence. Okay. And then key phrases. Like for example, this one is talking about a steakhouse located in NYC and how it was an enjoyable experience and when it was located and what are the contact details and stuff like that. All right. So it identified the language. It gives us key phrases like it's a online menu, great menu, dinner party, NYC, the name of the steakhouse, and the type of steaks available there, the owner there. Okay. Sentiment is with 86% confidence, it says that it's positive sentiment. Then it analyzes sentiment per sentence. Okay. And then it gives us something called as named entities, which is the names of places or geographical locations or addresses, or maybe a skill like for example, when I'm saying that cooking or some type of cuisines, so those are identifiable skills. So those it gives the named entities. And it will also give some contextual information about those entities, like for example, email address. This is a type of URL, or yeah, this is a type of email address, this is a phone number, this something could be a geographical location and stuff like that. Okay. So we also use this information to get named entities and key phrases. And these key phrases we use it as tags, and we use the information which is given by the LDA to build our taxonomy. So all these information collectively we use together to build our dictionary and feed it to our search engines for further, for semantic or synonym search. All right. So that being said, text analytics in itself is a very huge, comprehensive topic that deserves another session altogether. But this was, just a very high level overview of that. Now, coming back to topic modeling. Topic modeling, very simply put, is just identifying topics in a set of documents. What are topics? Topics are, language models which are used for discovering some underlying hidden text, which is what we call as latent. Latent text in latent structure in a collection of texts. So let's say I have a lot of documents, but all those documents are going to talk of something, right? Some theme, some kind of purpose, right? So, topic modeling is based on identifying what is the common theme or common things that documents collectively are talking of, and then it segregates documents accordingly. So, whenever I'm putting out a tweet, for example, so I may be talking of politics, I may be talking of entertainment, I may be talking of some technical stuff. So, these tweets could also be segregated by themes like that, right? This is what we are going to identify, what one particular document or corpus is talking of. Topic modeling is important because it reduces dimensionality. If you had attended the previous lectures which were conducted in the series of Introduction to Machine Learning, we had touched this topic briefly about dimensionality reduction, which means instead of analyzing a huge amount of word data which is available to us, it would be easier for us if we could break down our documents and then identify certain important keywords that can tell me about the document. So let's say this particular call report which analyst has given, and it is talking about how lucrative particular market in Malaysia is, or a company in Malaysia is for investing. And there could be a plethora of other call reports which are talking about the same sentiment: favorable market, favorable investment scenarios, right? So instead of going through each document line by line and trying to analyze and the sentence construction and word semantics, it would be easier for us if we could reduce the dimensions that we are looking at. So word count and TF, term frequency, image document frequency. So all these various things, instead of looking at that, if we could just look at the central theme or central idea of what the documents are talking of, we could still link the documents together. All right, so this is what it does. So topic modeling, it reduces the dimensions of the data, the representation for the data. It is unsupervised learning. which means, my very first point, how do you go about sifting through 550K odd documents and then, come up with tags for each document? We don't want to do that. So it is a perfect candidate for our scenario, unsupervised learning. You just feed the documents to it. You the topic modeling, it will, identify topics in documents and try to segregate documents accordingly. Okay, so it's unsupervised learning. And it is also used for tagging, so abstract topics that occur in a collection of documents. So let's say maybe, a set of documents could be grouped together in one particular topic because they are talking of things like tax and rebate and ratios and all the tax concessions or ESG things, corporate responsibility things. So maybe all these words come together in a topic, and all these documents could be tagged with these particular set of words. All right. So topic modeling enables dimensional reduction, unsupervised learning, and also tagging. And if we look at more use cases, so more real life use cases for topic modeling, apart from what we of course did in our workplace, so they are also used for article recommendation engines. Like I was saying, whenever you go purchasing on one, website or news site, when you're looking at one particular flavor of news, then immediately, you get certain recommendations or suggestions for those. Even in YouTube, when you're looking at one particular category of videos, immediately next time you open up your YouTube, you have similar recommendations based on those lines. Okay. And also, in Stack Overflow, they are used to identify the questions and answers. So a type of whenever you see in Stack Overflow, also you have tags at the end of each question, and this is catering to networking, or this is catering to Elasticsearch or C# or development or stuff like that. So topic modeling is also used to in Stack Overflow to analyze, question answers, tag them together. And recruitment industries to extract information from your resume and map you to particular job openings. And of course, in all the social media engines for mapping your tastes or recommendations or products or customer behavior to particular patterns, behavior patterns. And when we talk of a good topic model, right? So when a good topic model, it should be unbiased. For example, when I'm talking of apple, so now apple could be a fruit, but most of the time when I'm searching for apple on social media or Google or whatever, that would most probably, I'm looking out for Apple iPad or Apple products, mobile phones. Okay. So the model should not have any bias. It should not lean towards few particular keywords or searches. So each word that it sees in the document, it should treat it as a new word and try to think of how am I going to categorize this word. Okay, so when we talk of a good topic model, it should give me terms like health, doctor, patient, and stuff for the healthcare topic or healthcare segment. Okay, and same ways farm, crop, wheat for a farming related topic. So the documents which are talking of farm things or crops or soil should be segregated together. Text which is talking of health related things should be segregated together, so on and so forth. Okay. Now, why do we need topic modeling? So topic modeling basics are there, dimensional reduction is there, it's unsupervised machine learning. But why do we need? First and foremost is just a huge amount of data lying everywhere around us in forms of, our reviews or our tweets or our social media profiles, our even, office data, which we have, office documents, earning call reports, what you can say, the conference calls which customers have with clients and stuff like that. So we need a way to understand and this data and analyze it to make some informed decisions. So basically the motive of all intelligent systems is the same thing. See the data which is available to us and mark out some discernible patterns and then apply them for making decisions. So it is used is topic modeling is used for news flow aggregation, recommender system, stack overflow analysis, I was saying. And it could be also used for thematic, finding hidden thematic structure in the text. So, for example, if I'm writing a tweet or I'm putting out something on Facebook or on any social media channel, it has to. I mean, I'm writing about something. There's a motive behind that. Maybe I'm tweeting about my emotions. Maybe I'm tweeting about the recent happenings. So anything that you write about, it is going to fall in some particular topic or theme, and the focus of topic modeling is to gauge that, to understand the underlying pattern. Now we come to, there are many ways of doing topic modeling. The most available of them, and the most used of all the techniques available, is the latent Dirichlet allocation. Okay, let's break it down term by term. So when I say latent is what? As we talk of hidden structure. So something which is not very clear at the outset. Okay, so but there are hidden patterns, hidden subtext, and getting that something which is not available upfront to us, that is latent. Dirichlet, we'll come to this Dirichlet term. It's a very interesting term. So just for now, just take my the word for it. It's just a distribution of distributions. So it is it is a distribution of probability distributions. We'll come to that shortly, and we'll see how it works, the Dirichlet distribution. And allocation is nothing but, once we have the distribution, you are going to allocate it to the documents. Okay, so maybe this particular set of documents falls in this category, this particular set of documents fall in this category. So that is allocating. So you have latent, which is hidden analysis, hidden terms analysis, or hidden structure analysis. Dirichlet is a distribution, and allocation is finally allocating the Dirichlet distribution to various documents available in our corpus. Okay. When you talk of LDA, what it assumes is every document is a mixture of topics. Okay. So let's say we put our document through an unsupervised learning LDA process, and it finds out that maybe my all my documents fall in two categories. Say topic A, topic B, maybe say news and let's say movies, something like that, or global happenings and movies, this kind of things. Okay, and then we can when we identify those topics, what LDA is doing is it will assign that document 1 has a 90% probability of being categorized into topic A, and maybe only just like 10% probability into topic B, something like that. Okay, and every topic, so when I'm saying topic, right, you it is just like a collection of words. So don't take it as something which is I'm saying news as a topic or entertainment as a topic. No, topic is just a collection of words. So let's say there are particular documents that are talking of a theme which centers around steel, iron ore, gold, copper, and all these metals and ores of metals. Okay, so there are documents which are talking of finance stuff like ratios, investment, corporate governance, government policies. There are set of reports which are talking of terms like solar energy, green energy, corporate social responsibility, and stuff like that. So each of these collection of words together will form a topic. Okay, so whenever I'm looking at a new document and it has the word, let's say, renewable energy. So the LDM is going to analyze that which set of words it should more probabilistically belong to. So now if I have a set of words which are talking of solar energy, green energy, and ESG and all those things, then of course when a document comes in which has a keyword renewable energy, then logically it should belong to that set of words which are thematically or semantically related. Okay, so entertainment topic may be made up of words like movies, television. Okay, and of course there are words which could be common across topics. Let's say in our case, for example, if we take the call reports, the word product, the product word is so common, and it could appear across sectors. So a product could be a industrial product, a product could be a financial financial products, a product could be something which is related to some chemical industry, so product of some chemical reaction. So I mean those kind of words, either then we choose to exclude those words from our list of from analysis altogether. So remove them as stop words if you think that they could be misleading or they could cause a lot of chaos, or simply just let them be, because there could be words which could be occurring across topics, okay, which could be common across topics. Now, before we go on to the concept of topic modeling, that is how it happens, how how the topics are identified, how do I actually machine learning, how does it unsupervised machine learning, what does it do to actually break down the documents into a group of words? Okay, so before we do that, there's a very interesting concept called as Polya's urn. Okay, so it's a sampling technique used in probability. I won't bore you with the mathematics. So just let's get the concept clear. And we say that just imagine that you have a urn or container with red and green balls. Okay. Now you can choose one ball at random. You see the color. So maybe if I'm picking a red ball, you note the color, and then you replace the ball along with another ball of the same color. Okay, and this resulting model, so if I take a red ball, I replace it with another red ball, or if I take a green ball and don't replace it at all, possible, right? So this resulting sampling technique is called as Polya's urn process, and this is the basic principle what is used in Dirichlet distribution also. Okay, so how it is used in Dirichlet distribution? Now, in Polya's urn, there were balls of only two colors, maybe red and green. In our case, just imagine that instead of the urn, you imagine you have these 550K documents. Okay, so those are our urn. Okay, so you have infinite number of colors available there. So you start out with an empty container. You randomly pick a colored ball. Maybe I pick a red color ball and place it in the container. Okay. Then for the next ball, I have two options. Either I pick a colored ball and I place it in the container, or I remove randomly a ball from the container and put it back with another ball of the same color. So what happens is, as the number of the balls in the container are increasing, the probability of every time picking a new color decreases, right? So what happens essentially is, after some time, like if the when the LDA process goes on iteratively, there is a less probability of picking out something new, which means you have reached your point of what is that? The maximum point, and you cannot be segregated further. All right. So this is when you have already formed categories. So you've already picked all the possible new color balls you could have, and now all the balls which you have are almost segregated into categories of having similar color or similar properties. So this is a Dirichlet process. And when you talk of the LDA algorithm in itself, what it does is, now you extrapolating the analogy to our actual documents, our corpus, our text corpus. So at the outset itself, we said, right, that LD assumes that documents are nothing but mixture of topics. Okay, then the topics are based on some kind of words. So maybe when I'm talking of one particular set of documents that are talking of real estate or energy, they might have some specific words. Documents talking of some other theme might have some different set of words. Okay, so given a set of corpus, what LDA does, it tries to figure out what topics would create those documents in the first place. So if I had a set of documents talking of finance related thing, so they would fall under keywords which are talking of tax and profit and loss and those kind of things, balance sheet and general ledger. And then LDA, what it tries to do is, if I had a topic having all these words, what documents would be candidate to fall into those particular categories? So if we have to represent it, if you see, this is nothing but a collection of documents, so D1, D2, D3, and this is the collection of the words in the document. Okay, so maybe the word W2 occurred two times in document one, and so on and so forth. Okay, so the each word by word, how we do it in TF IDF, term frequency inverse document frequency, each word in what frequency it appears in the documents. Okay, and then LD, what it does, it converts this into two matrices. So this M1 matrice is nothing but it is documents, and the topics. Okay. And then the second matrix is the topics and the words. So topics is, just imagine that there are two topics, T1, T2, or imagine three topics, T1, T2, T3. Now document one is under T1 because most of the words that are in document 1 are a part of the group T1. Now, T1 could be, words like, let's say, if they're talking of energy sector, it could be something like, energy savings or solar or those kind of. So topic 1 has those kind of words. So the second matrix, it is mapping the words and the topics. So the word, let's say the word product, it occurred in topic 1 and it also occurred in topic 2. Okay, the word. So this is the mapping of this is the matrices which LDA constructs for us. So it constructs, just for brevity's sake, I mean repetition's sake, it constructs documents and topics and the words belonging to those topics. Okay. Now, let's say, for example, when I'm coming across a new word. Okay, so now, for example, so each word in each document comes from a topic. So when we say that when I'm analyzing a new word or a new document, I'm going to just say that this is going to belong to a new topic. And then finally, I calculate a probability that given this word in this document, what is the probability that this will belong to one particular group of words in one particular topic. Okay, so you have the first probability, which is a distribution of topics in the documents. The second matrix which we saw, the first matrix was topics and documents, the second matrix was words and topics. Okay, so we can say that probability of a word in a document is equal to the first probability into the second probability. Okay, so probability of word in a topic and topic in a document. This is essentially the mathematical breakdown of that. Okay, and if we had to understand that with the help of an example, so let's say we are saying that we have a random sentence which is India enters World Cup final, and each word has been categorized here. So let's say India enters World Cup and final has been categorized as into a topic. So India belongs to topic 1, enters belongs to, maybe this word belongs to topic 3, world belongs to again topic 1, cup belongs to topic 2, final belongs to topic 4. And in each of this, the count is shown. So how many times India appeared in a topic 1? Okay, how many times it appeared in topic 2? And how many times as a part of topic 4 it appeared, something like that. Okay, so this is the count of words. Now let's say we are analyzing a new word in a document. So I come across again the same word world. Okay, but it is a part of a new document. What LDA does, it doesn't assume anything. It says that it is a new word. I don't know what topic it belongs to. World may be already categorized as a part of topic 3 or whatever it is, but maybe now when I'm analyzing the word world in a new sentence, I say that, hey, I don't have any idea which topic it belongs to. Okay, so what it does is it will first represent all whatever information we have. Okay, so first the information we had was was India, I mean the words and the topics that they belong to. Okay, so this is what it did. The topics it words belong to, and then how many times each topic is assigned to this word. Okay, so how many times that a topic has been assigned to that one particular word. This is what we plotted. This is what LDA plots. Okay, and then when we are multiplying the matrices, so now if you look at world, right, world appeared in topic 1, and world appeared 28 times in topic 1, it appeared 4 times in topic 2, 12 times in topic 3, and only once in topic 4. So as I was saying earlier, the topic words need not be exclusive, mutually exclusive. There could be repeated, but probability of, when I get a new word, what is the probability that it will fall in one particular group of words is what LDA is calculating. So logically, when you see that when they are going to multiply the probabilities of topic given document and word given topic, then you are going to come up with the first, right? So the new word world logically should belong to topic one because it has occurred the maximum number of times, the 28 times under the words which are grouped under topic one. So whenever I mean coming across a new word in another document, logically assuming that I don't know what category it falls under and calculating all this probability distribution, I'm going to land up with the same P1 into P2. When I calculate the probability, it is going to give me the topic one itself. And then you iteratively refine this process, and then finally you achieve a state where the topic and term distributions are good enough, you cannot refine them any further, and that is the point of convergence which we call for LDA, which means now my model is quite stable. It has already identified the possible number of words which could belong to a topic, and how to, there's no further segregation is possible, and that is when I have a model available with me. So this technique of assigning weights and making an unbiased model, so that you don't have any inherent biases. Like I was talking of Apple, iPod, and then all the things which are talking of Apple or iPod together are termed together without any without having any relationship also. So just to talk of Apple, and it automatically goes to topics which are talking of mobile phones. It's wrong because Apple could be in the context of a fruit as well, something like that. Okay, so to avoid this kind of a bias in model, Git sampling technique is what is famously used for LDA. And when we talk of fine tuning LDA, there are some parameters which is called alpha and beta. So alpha is the document and topic density, beta is the topic and word density. As these values become higher or lower, the alpha or beta values, then you can, understand that what actually, how good your model really is. So if your value of alpha is more, then which means that I have a lot of topics. So which means in one particular, let's say like a group of documents which I have and I feed it to the LDA, if the value of alpha is higher, means that there are a lot of separate themes under which my documents fall, and they are talking of many things which may be mutually exclusive or not. So there may be keywords which are occurring inside of most of the topics. Like for example, I said the word product. Product could be a part of a number of topics ranging from finance or energy or real estate or chemical industry. Okay, and higher the value of beta means there are many number of words that describe the topic. So which means when I'm talking of finance sector, ideally, there may be there should be like maybe 15 to 20 words that should immediately give me a sense of my topic being that of finance. For example, profit, loss, balance sheet, ratios, financial ratios, and general ledger, all these things. But when the beta value is higher, there could be a lot of words which are describing that topic, and that could also result in a lot of chaos. So you have a lot of overlap between different topics, and you cannot discern correctly, the document, new incoming document should fall under which category. All right. So just to show you our LDA model which we built. Okay. I'm sorry. Oh, sorry. Our models were uploaded in Teams and synced together, so that's why I have those. Okay, right. And let us look at okay, so let us look at, for example, now as I was saying, all our call reports which the analysts write, they fall under 11 sectors. Okay, so these are something: real estate, materials, financials, energy, information technology, utilities, healthcare, communication services. Okay, so 11 sectors. So what we did was, we inside each of the 11 sectors which we have maybe around 1,000 3,000 documents, sorry, 15,000 to 20,000 document per sector, and then we run the LDA on each sector. So let's say for real estate, if there are around 10,000 call reports or documents talking of real estate, we run LDA on real estate, and inside real estate, it will then further identify topics which talk of a particular stuff, which particular theme, particular set of words, and group documents accordingly. Okay, so let's look at maybe materials. Okay, let us look at materials, and let us look what LDA gave us, and what all what all topics it built, what all set of words it gave to me. All right, so if you see that here, if you see the LDA, there is a lot of overlap between the first six topics, and the topic 9, 8, 10 onwards, I mean 7, 8, 9, 10 are pretty mutually exclusive. So there are terms which absolutely do not fall under and mutually exclusive terms to these topics only. So if you get something of this sort, where the topics are quite quite spaced out, so which means that you have a good distribution and not much overlap, and your model has identified documents correctly. Okay, documents and topics correctly. So let us select topic 1. Okay, when I select topic 1, what it is talking of terms. So these are the related terms which is talking of, say, year, government, coal, word, start, power, expect. So this is a material sector, and inside that it created certain topics, and the topics are talking of few of the first topic is having a set of keywords which are talking of all these things: year, cement, government, nickel, need, end, currently, stuff like that. Okay, maybe let us go to topic 5. Topic 5, inside real estate sector only, is having keywords which are, talking of price, volume, increase, high. Okay, so increase, high, sale, right? So, which means, it could be talking of copper production, or rise or volume of copper production, something of those things. Okay, let us look at topic 7 in the material sector. And here, if it is even more, the words which are allocated to topic 7 make even more sense. For example, steel. Okay, raw material. It talks of cooking coal, domestic, then inventory. Okay, so steel inventory, coal, cooking, all those things. Again, if you see product word is very generic. Okay, and we realized it after running the model that this product word doesn't occurs across documents and across sectors, and it doesn't really make any sense. So I mean, as we go further, I told you that we'll refine the taxonomy, right? Let us look at topic 8. 8, in fact, even makes more sense where it talks of construction, project, infrastructure, petrochemical, and industrial, commercial, all these things. Okay. Now, when we are building the taxonomy, right, we cannot look at all the words. So what LDA gave me is under one particular topic, what set of words are occurring. So under this topic 8, all my documents are talking of logistics and construction projects and infrastructure and materials and stuff like that. How to take words from these and build my own taxonomy is something up to us. So it just gave the words which are occurring, and that majority of the documents falling under topic 8 are talking of this thing, or maybe falling under topic 9 are talking of steel price. Okay, so these are all. If you see, let us look at. Okay, let us look at other topic. Maybe something like financials. Let's say financials. Yeah, see, in financial sector, you see that most of the topics are quite spaced out. Okay, so let us look at topic 4, for example. Okay, topic 4, you will see of it talking of ratios like talking of things like year on year, equity, volume, revenue, okay, exchange, result, derivative. And if you look at topic 5, you will see talking of loan. Yeah, you will see of talking of loan, credit, then mortgage, rise, DPS, single digit, all these things. Topic 6 talks of again, the financial aspects like the sector, private equities, insurance, inflation, okay, the inflation spread, equity investment. Topic 7 talks about, topic 7 talks about stuff like, the yeah sorry, the impact, economic impact, corporation, devaluation, right? So you see that the documents here, in even inside one particular sector, are categorized into topics which are talking of a set of words. And now using these using these topic modeling techniques, the group of words and the topics which are given to us by the LDA, now we are going to build our own taxonomy. Okay, so let us look at topic 1. Okay, now topic 1, it is most of that, it is talking of branch government. Okay, Aspos is the software which we use to create PDF out of Word documents. So that word it is using. Okay, then it is talking of buy, sell, small asset, and those things. Okay, so if you see that within a particular sector also, it has categorized documents, and it has given me a sense of what group of documents are talking of what sort of theme. And depending on those things, I'm going to build my taxonomy. So now whenever, let's say, I want to search for documents which are talking of maybe, for example, ratios, financial ratios like year on year sales, or ROI or ROE, then maybe I will have the documents which have all those ratios like EB, ITDA, and DPS and EPS. And maybe if one particular analyst is looking for ROI and ROE, I can give him suggestions for, do you also want to look at documents which are talking of EPS or DPS, or he's talking of increased production. So do you also want to see documents which are talking of increased sales or upward trends in particular sector or sales or stuff like that? Okay, so this is how I can now feed my search engine synonyms to my search engine. So whenever you're talking of inflation, then you should also talk of government taxation rates there. Or whenever you're talking of currencies, then you should maybe talk of USD, HKD, and those kind of currencies available to me. So yeah, at least I now have a fair idea of what my 5 million documents are talking of, and how they are, what words they are composed of, and how they are going to, and I begin to have a bit of understanding about what all my zero point 0.5 million documents are all about, and how I can group them. Or let's say I have a new incoming call report which is posted by an analyst, then roughly it should belong to what topic, what it is talking of. Or maybe it could so happen that once this LDA model is available to us, we just keep on, rebuilding it every fortnight or every month, so that new call reports which are made available might form a separate topic altogether. So maybe even in the, like I was saying that even in the insurance topic, where I have keywords like reinsurance and policy and claim, I could maybe have a set of other documents which are now talking of insurance fraud and fraudulent claims and fraudulent transactions, or those kind of stuff. So it could so happen that, so that's why we say that it is an iterative process. So I keep on building the taxonomy, I keep on refining my dictionary, I keep on, running the LDA time and again, maybe month or 6 months or 5 months, depending on the volume of all reports which we see, which are uploaded every day. And then we keep on, refining our LDA also. We keep on refining our taxonomy also. And I totally agree that not all the words here might make a lot of sense. Okay, and there could be words which are a part like loan. Now you see, loan was a part of most of the topics which we saw here, right? So here also in topic 6 also you had the same thing, like yeah. So yeah. Now topic 6, if you see, it is talking, if it is gathering all the banks together. So you have RBI, ICICI, HDFC, and you have all the currencies, INR, and all the non-performing assets, NPA, and rural areas and stuff like that. When you look at topic 7, it is all about the inflation and government terms and macros and stuff like that. Topic 8 would be again ROIC, value, hold. Yeah. So just it makes a lot of, it gives me a lot of insights about structure of my documents without me having to individually sift through and trying to tag documents by myself. That would be a very time consuming and again a very subjective process. So I feel that one particular document is talking about maybe chemical sector, but it could be from others perspective, it could be talking of pollution created by chemical industries, and they could tag it differently. So that's a very subjective process. So when we introduce LDA, it is unbiased, it is objective, and it is just going to mathematically, without having any personal bias around it, it mathematically categorize and term your documents and topics and group of words, and accordingly group your models and documents. Excuse me. So this was how the LDA results which were given to us. And whenever you're now you're calling the LDA, so you have a GenSim library which has the LDA model method. Then these are the parameters you're going to feed it: alpha, beta, number of topics, okay, number of topic terms, and number of iterations. Again, coming to the number of topics, in our case, what we did was we said that you identify maximum, I think 15 to 10, no, yeah, sorry, everywhere you see that there are 10 topics. So even if you go to the previous consumable sector, if we go, everywhere you see that, yeah, let's go to health industrials. Okay, everywhere you see that we have 10 topics. So what we did was, because our document size, as I was saying, that it is more or less, not very huge. And we know that the call reports run maybe 1 or 2 pages, maximum 3 pages. So we thought that a group of 10 topics per document should be enough. As you see that most of the keywords are segregated in the first 1 or 2, 3 topics, and then they are spaced out the 7 topic onwards. And then when you see, go to the 10th topic, the number of keywords also anyways, they are decreasing. If you see here, the number of keywords are also, they are like decreasing a lot. So it's like only 0.4% of the tokens if you see top 30 most relevant terms. So we identified, like we said, that every document you try to, every group you try to segregate it out into 10 topics, and maybe 30 terms per topic. And we went with unigrams, so which means the document. So let's say by document is ICICI Bank is registering declining sales. So ICICI Bank registering declining sales. All these are split into unigrams. We are removing out all the stop words and doing lemmatization, tokenization, stemming and stuff, all the NLP stuff. And then we are constructing word by word. So there are techniques like, maybe you could club 2 words together. So bigrams or trigrams. So like corporate and governance. Instead of doing those 2 words separately, corporate governance is something like one particular term could be seen as one particular term, corporate governance, or corporate strategy, or political strategy. So those kind of things, you could even have bigrams and trigrams also. And we are also, right now in the process of building bigrams and trigram model. This one is a unigram where, each of the words are taken one at a time, and they are used as to make the topics and form the words. So per topic 30 words, and per section meaning per sector, healthcare or whatever is that, we are having around 10 topics, identifying 10 topics. So that also could be, something like we might try to have more, instead of 30 terms, we could try having 50 terms so that the topics are more spaced out. And instead of 10 topics, we could try having lesser topics, maybe 8 or lesser, or maybe more topics, something like that. So those things are our trial and error, and as and when we are building the taxonomy and getting more precise results, we are in process of doing that. All right. So these are the number of topics. When I say we set the code at 10, norm at 10, and per the group of words per topic was at 30, and number of iterations passes. Okay, so we put it as at 10. So it did a 10 passes on our 550K documents. Implementation. So this is I will be sharing the presentation, and you have a complete link to the Jupyter notebook. So you have loading data, you have cleaning, exploratory analysis, preparing the data, model training, and analyzing the results. All right. So if you look at the code file for that, so this is what you will essentially find in the GitHub. Okay, where we implement. So the code itself is not very huge. Okay, you are using Gensim and you are using NumPy and Pandas. Okay, so these are our sectors which we're talking of: communication, discretionary, staples, and energy, chemical, or those things. Okay. And these are the of course, I will not in the GitHub I have shared some demo documents, because these are all corporate documents. So please, you whenever you are trying to get the GitHub code, you please change the path accordingly to point to whatever corpus you are trying to train it on. Okay, I will of course not be sharing the corporate data here. And then when you are doing, let me just we are removing the stop words here. See, your NL ticket or download stop words. You are removing the stop words. You are you are defining your own stop words also. Like for example, I said that created, evaluation, then and with, full version, product, and all these things, company, business, because we are an asset management company, business, margin, capacity, profit. These are all things which would be occurring across your documents, across sectors, across topics. So you can, we define our own stop words which we don't want to be presented as a part of our results. And then when you are training that, so these here in this piece of code, you will see that you are constructing bigrams, unigrams, trigrams here. Could be clubbed as bigrams or trigrams. Okay. And the results which I showed you were for unigrams. The code here allows for bigrams or trigrams also. So it's a more sophisticated version of the code. Unfortunately, the HTML files which I showed you were for unigrams, because the bigrams and trigrams is still the training is still ongoing. It takes around 8 to 10 hours for 550K documents for 10 passes, or now we even revise the passes, it's 50 passes. Okay, so you are doing lemmatization and tokenization here. Here, see, lemmatized. Okay, and then finally, when you are building the LDA model, you are giving the corpus, which is the number of documents per sector. And then you are going to update every, so which means the learning, right? The learning, you are updating every single pass. If you set it as 0, which means it's a batch learning, so you are putting the documents in batches, and then you're not going to update the learning rate or the learning or the topics also, for that matter. So once for one particular 50 documents, you are identified so many topics. For the next 50, don't try to refine again. So this is update every. So we are updating every single pass. Chunk size is 50. Passes is 10. As I was saying, it will have 10 passes. Alpha, the parameter for the document and word topic density, it was set at auto. And per word topics is another important parameter which is set as true. Okay, per word topics means whenever I'm coming across a new word, should I assume that it is a new topic and then try to calculate the probability distribution of putting that word in either in a new topic or in existing topics. So that I've set it as true. which means that, if I come across a word product, okay, I will assume that I don't know what topic it belongs to, and now I'm going to calculate a fresh probability of putting it in an existing or a new topic. So that is a per word topic or topic parameter, which is true. So these are the parameters which we had discussed about for in the LDA in the right, and then yeah, and this is where you get the model. So this is and finally, once you get that, we ran some HTML files on that, to HTML code on that. So this one, see, to shows the results in terms of those charts and the term frequency and what are the words and what are the topics and stuff like that. All right. Now it doesn't stop here. So LDA just gave us one particular approximation of what all our documents are talking of, what are the topics, what are the words inside each particular topic, and how my documents got grouped together under those topics. So I have some understanding, or at least a semblance of understanding of what data I have, right? On top of that, once I build my taxonomy, we are essentially, if you have heard of word neural embedding techniques like word to make, what we plan to do is something similar. So let's say if I'm talking of something like robotic cars, or when I'm talking of something like raining, it should also give me search results or at least related results for umbrella, raincoats, or rain related stuff. All right. So I just want to briefly touch upon what we are trying to achieve. Okay. Let's go to word embeddings. Okay. So maybe if I'm searching for lithium here, and I don't have an exact match for lithium in all my call reports. So analysts are just randomly searching for call reports inputted by them or by others, and then they don't really know what documentation is there and what exact keywords are there. We would want to have something like this. So if there could be an exact match lithium, there could be application of lithium like lithium ion batteries and stuff like that. And once I do that, so let me just check lithium ion batteries, and if I do a show nearest, it should give me batteries, then solar cells, acid batteries, nickel metal hydride, rechargeable batteries, and stuff like that. So essentially what I'm trying to do is I'm trying to identify all the words inside one particular topic, which are, so ideally these all should have been available inside one particular topic, and now these all form my dictionary. So when I'm searching for lithium ion batteries, it should also point me to documents which are talking of rechargeable batteries and nickel metal hydride, because essentially these were falling under the same topic. All right. Okay. Let us look at some other stuff. So when I look at rubber, then it should give me rubber, of course, rubber related bigrams, synthetic rubber. So this was a unigram. It should also give me bigrams, related bigrams, synthetic rubber. It should give me resin. It should give me polyester. So everything which is related to or around that particular word. So ideally, my LDA would have identified one particular topic, something like just maybe material for clothing material or something of that sort, and then it would have given all these keywords as a part of that topic. So now whenever I'm searching for any of the candidate keywords from that topic, I should be able to find all the other related keywords also as synonyms to that. Okay, so this is roughly what we are trying to achieve, and almost there. As you saw, the LDA was there, and now we will give the LDA, will build our own dictionary, and they'll combine it with the word to vec embedding, the neural embedding. So I had covered this topic in the NLP techniques, which we discussed in Introduction to Machine Learning Series 3. And so word to vec or the taxonomy is already existing. And on top of that, we are feeding it our own taxonomy, as we discussed here, the topics and the words which are given. And this is what we plan to achieve. So let's say I try something like this, king also. So show nearest, it should give me monarch, crown prince, bigrams also. Okay. But it could be a sultan in some other language, royal throne, right? So all these related words, related terminology. So this is what we called as word semantic analysis, word semantic generation. Let us try. And then right now, it is not there in the vocabulary. So it is not fed in the vocabulary, maybe just robotic, and it is giving me a humanoid or robotic arm, maybe bionic, yes. So good approximation, good semantic analysis. Okay, and then just to to show what it does is basically when we are talking of semantic closeness of words, we are trying to compute the distance between the cosine distance between words. So the more similar the words are, the angle between them will be zero. So the cosine will be one, right? So for example, if I'm talking of say neat and clean, and if I show the similarity, I think it has to be like this. Okay, neat and clean, then it shows that they are I mean it's only like the closeness between them is only at 29%, which is correct. Like they are not very semantically same. I mean they don't mean the same thing. Neat is one thing, clean is one thing. Maybe if I put hygiene here and show similarity, still it is like at only at the 30% closeness, right? But if I put here a totally diametrically opposite stuff, it is hygiene and dirty, or maybe I'll just say clean and dirty, then they are like quite apart. So they are so clean is in one half, dirty is in another half. Okay, so the similarity of words is computed, so which means how close the words are together. So if they are poles apart, the similarity will be -1, and if they are very near, almost meaning the same thing, the cosine distance, the angle between them will be 0 and the cosine will be 1, right? So this is what we are aiming to achieve. Okay, so this is what with LDA you get the related terms, you feed it to your dictionary, and then you try to compute the distance between words so that all semantically close words or same meaning words will be all available together at one part. There is a second stuff also, which is like word analogy, right? Word analogy meaning something like if I say air and bird, then water is what? So it was like water is fish, right? So I mean, if I'm talking of birds flying in air, then fish swimming in water. So I tried something like America is Republican, then India is what? So it gave Democratic, GOP, something like that. Okay, let us try king and man. Okay, then queen, and then if we show that, oh, sorry, excuse me, yeah, could be it's a girl, right? So king is a man, then queen is a girl, something like that. So word analogy also. So maybe if I'm talking of loss making companies or COVID-19 vaccines, then it should also try to establish analogy between them. So maybe if there was a vaccine for some particular outbreak earlier, and then I try to put an analogy for COVID-19, it should try to understand the context which I'm talking of, the context in which I'm talking of, and try to return me search results accordingly. So this is the most ambitious of our aim to achieve. But the first two, which is getting the semantically similar words and closeness between similar meaning words or contextually similar words, this is something which we are almost there, achieving there. And the code you can find on my GitHub. And so we hope to refine our search results and get to our golden aim of being of building a internal smart document search and semantic analysis engine. And so I hope learned about topic modeling and why we have to use it, why did we use it, and what all use cases it tries to solve, it tries to address. And I would be happy to take any questions if there are any.
There are questions on the chat. Thanks, Priyanka, for that informative this thing. So one of the users asked, so what is the tool used to generate this dynamic visualization of LDA clusters?
Mm-hmm.
Although they answered it that Pi LDAVs.
Yes.
Um, do you have some more inputs on that?
Okay, so the library which we used here was built by our own data science team. Okay, so that library I mean, they have built on, it's a custom library they have built on top of some existing ones. Okay, so I mean, once I share this, you should be able to download that. But yeah, there are a lot of other libraries out there which are available for representing it as HTML. Okay, so this one is by L Davis only. But if you see that there are some customizations our team has done there to hide a few things. Okay, so the way it is presented, there are a few customizations we have done. So yeah, so that is I mean, apart from that, there's nothing special we are using. Yes. And the second question is technique that would
Cool.
possibly, what
Thanks for
will be
that.
the, yeah. And I see one more question is modeling technique that could be possibly used for doing the subject matter text analysis. I'm looking at high level suggestion. Okay. So, see, the thing is, when you talk of subject matter, so for example, you have to, I mean, if you don't want to really go and have your NLP experts or your analyst really go through documents and try to dig out some keywords or key phrases, then you have certain licensed dictionaries. So what we did was to enable us to build a robust taxonomy, not only with the use of LDA, but there are certain licensed information sets that we downloaded from Reuters, from Bloomberg, from Financial Times, and from other domains which talk of ESG and which talk of green energy. So there are a lot of paid versions, paid data sets which you get that will group together terms talking of financial industry or talking of just maybe consumable staples or real estate. And that is how we without having our analyst to spend time on these things and going through documents and trying to extract topics or keywords, we actually paid license fees for these data sets and got them. So yeah, so that is what we are using. But there's no special topic modeling for one particular subject that we are using. So as I said, we use the text analytics for getting the keywords and for getting the sentiment text key phrases. But apart from that, yeah, we are getting ready-made taxonomies, dictionaries from licensed vendors.
Are there any other questions? You can put them on the YouTube chat, or if you're watching this on Facebook, then on Facebook chat. All right, we have come to the end of our session, and it was glad that most of you could make it. There were a little bit of hiccups with the link, but to make sure that next time we don't run into issues, make sure you subscribe to the channel. So as soon as we go live, or we create a new live event on YouTube, you will be able to do that, and we will see you next week. One more thing that I'll ask again is, if you have any other comments of what you want to learn going forward, then I would strongly say, again, put those notes in the comments. We will be reviewing them and going back and figuring out how and when do we time that. So till next week, thanks all for joining in. It was wonderful to have you. Thanks, Priyanka, for the wonderful session. Thanks a lot.
Thank you, guys. Thanks, Setu, and see you all next Tuesday.
All right. See ya.
Okay. Yeah. Thank you.